Okay, so in this unit, we've been learning about how objects attract one another through gravitational force fields, how to figure out the size of that gravitational force field, and how it affects things like the speed of the object, which tends to get people confused when they're thinking about things that occur on Earth. Okay, because the size of any gravitational force field, which is Fg, is equal to the gravitational constant times the size of one of the objects times the size of the second object divided by the distance between them, or the radius of their orbital period, squared. Which tends to get people confused because this formula clearly tells us that if we have two objects that are larger, the force of gravity between them is going to be greater. So if, for example, we drop an apple, which we'll call mass 1, above the surface of the Earth, and we drop, on the other hand, a car above the surface of the Earth. This is a very terrible car. I apologize in advance. In this particular case, the car should experience a greater force due to gravity than the apple does because the mass of the car is greater. And if the force due to gravity is greater, then we have another issue with this formula, which if we change force is equal to mass times acceleration around to calculate for the acceleration, we end up with force divided by mass. So if we're increasing the force that's acting on an object, we should end up with a greater acceleration, right? And this follows if we even plug some numbers into that formula. So let's plug some numbers into that first formula. Let's simplify g, and we're just going to make g 1 because we're not really trying to see the effect of g on these numbers, so we can simplify it and make it something easy to work with. Let's say the mass of the apple is 1 kilogram, and the mass of object 2, which is Earth, I'm going to simplify as well. I'm just going to say it's 5 kilograms, just for the sake of simplicity at looking at how these numbers are going to be affected by changing mass 1. And then we'll say the radius between them is the same, so I'm going to call that 1 meter as well. Right, and for our second problem, we've still got g as 1. The mass is going to increase in our second problem because now we're looking at the mass of the car as mass 1 as opposed to the mass of the apple as mass 1. So the mass of the car, I'm just going to double it. I know that cars are not 2 kilograms, but I want to make it clear what happens if you double the mass of the first object and how that affects the outcome of your formula or your calculation. The mass of the Earth is going to remain the same in this particular experiment, so it's going to be 5 kilograms, and the radius is still 1 meter. So if I take those numbers and I go and I plug them into a scientific calculator, I end up with 1 times 5 in the first one divided by 1 squared. So for this first force of gravity between the apple and the Earth, my force of gravity ends up being 5 newtons. And for the second situation between the car, I end up with 1 times 2 times 5, which is 10, and then divided by 1 squared again. So the force of gravity between the car and the Earth is 10 newtons. So as we can see, increasing the mass of the object does increase the size of the force between those two objects. So again, this is confusing for people because acceleration is equal to force divided by mass. So if we increase the force and we make that larger, then we should be seeing an increase in acceleration as well. But the issue in that theory lies in the second part of this equation, which is the mass, right? As we can see, we've changed the mass of both of the objects in this formula, which means they change in this formula as well. So if I take a look at that first situation between the apple and Earth, force or acceleration is going to be equal to the force being exerted on the apple divided by its mass. So in this case, it's going to be 5 newtons divided by the mass of the apple, which is 1 kilogram, which means the acceleration is going to be 5 meters per second squared. And if I go back down to here and do the same thing with my car, the acceleration of the car is going to be equal to the force exerted on the car divided by the mass of the car. So I get 10 newtons as my force, but this time my mass has been doubled and it's 2 kilograms. And if I divide 10 newtons by 2 kilograms, I end up with that same answer, that the acceleration of the car is going to be 5 meters per second squared. So the acceleration of these two objects is exactly the same. This also makes sense if I start to substitute in some of those values into that force equals mass times acceleration, right? There's two ways that I can look at that one. The first one is by substituting the force of gravity in between all objects, right? So the force of gravity is going to be equal to g times the mass of the first object times the mass of the second divided by radius squared is going to be equal to mass times acceleration of the first object. All right, as I can see on both sides of this equation, I've got the mass of the first object. So in this particular example, the mass of the first object is not going to have an effect on the overall acceleration. The only thing that's going to have an effect on its acceleration is the size of the Earth. And because they're not orbiting, the radius doesn't really come into a play here either. So the rate of their acceleration is really due to the universal gravitational constant and the size of the Earth. The other simpler way I can do some substitutions for this formula is on Earth, force is equal to mass times acceleration. The force that all things are experiencing on Earth is equal to their mass times their acceleration due to gravity. So I end up with the formula F is equal to mg, which is equal to ma. Again, we can see that the mass of the object is on both sides, so we can delete it. So the acceleration of all objects on Earth is going to be equal to the gravitational constant. All right, this one's a little clearer because the objects that are falling on Earth are not orbiting. They're not experiencing circular motion. So this idea of them having a radius is not correct. But here we can clearly see that the acceleration of all objects on Earth ends up being equal to that gravitational constant, which is g. Okay, hopefully that explains why all objects on Earth fall at a similar rate. It's due to the kind of proportionally opposite reactions. Yes, the larger objects will experience a greater force, but they'll also experience less acceleration because their mass is greater. So changing the mass does increase the force, but it also decreases the acceleration a proportional amount.